So my name is Chintan Turakhia. I'm one of the engineering leads in Marketplace. And behind me, you can see a pretty fast-paced picture. This is actually a time lapse of Uber's designated parking lot from Super Bowl 2017. And this is a great representation of how and what Marketplace is setting out to do in a real-time physical world for Uber. It's great to see people leaving the stadium, taking Uber to get home and to get home safely, but efficiently. So what is the Marketplace? The Marketplace is the real-time algorithmic decision engine behind Uber. Think of it like the brains behind Uber. When you open up the app, you type in a destination, a fare pops up, 10 bucks for an Uber X, great. That's a combination of real-time machine learning algorithms and services delivering that information to you based on a dynamically changing physical world. You click request Uber X, and you'll see that screen pop up where you as a rider are being matched to a driver. That's another set of real-time machine learning algorithms that are working at scale to make that match possible and to let you get to where you need to go. In the Marketplace, there are a lot of models that we have, and we have sort of this split. We have models that describe the world, and we have decision engines that act on those models. And what's interesting is kind of what Waleed was talking about. Uber's problem space is a space-time problem. It's a physical problem of movement of things around our world. And so the better we can model the actual physical world, the better our Marketplace decision engines can enable a better rider and driver experience, as well as create efficiency for Uber's Marketplace. So there's a lot of great work happening in Marketplace. And all of that work is focused on real-time decision-making using machine learning in response to the physical world. But we'll only have a chance to talk about 3 examples today: forecasting, personalization, and dispatch. Forecasting is focused on predicting the future states of the marketplace, looking at supply and demand. Personalization uses machine learning to enable a unique rider experience at the right time, at the right place. And dispatch. Well, without dispatch, you wouldn't be able to get to where you need to go. You wouldn't be able to get matched to a driver. And so here are 3 examples we'll talk through where we're leveraging machine learning at scale to enable an efficient Uber marketplace. If we don't have foresight into the future states of the marketplace, our responses to the world can be reactive. They may not be extensible. I mean, you may have already experienced this in the past, where the demand may be high, you see that surge multiplier pop up. That's not a great experience, and that's a reaction to an imbalance in the marketplace. And if we continue to be reactive, we're like this cat. We keep just squashing hotspots. And what we're really trying to do by leveraging machine learning that allows us to differentiate ourselves is to make all of our marketplace decision engines future aware and future changing. The challenge is, how do we see the future? Let's start with forecasting. In marketplace forecasting, we deliver real-time forecasts for supply, demand, and other quantities like airport foot traffic based on flight time arrivals. We do this for a given space, and we do this for given time horizons. Think minute-level forecasts for the next few hours. Think hourly forecasts for the next few weeks, but across space and time and multiple quantities. So here's an example of where we do use machine learning in real time. We take the input stream, a lot of the data that Waleed already spoke about, and we take this and stream it into our forecasting engine. And our forecasting engine will do 1 million space-time transformations to sort of stretch out this time series. Let us look at historical data and recent data. And our models can range based on the use cases and the needs for the decision engines. They can range from linear models to gradient-boosted decision trees. As these forecasts are generated, we have models for every city that Uber operates in. And these models can actually be specific to spatial clusters that we have. We generate these forecasts in real time for our pricing engines. And the better our forecasts are, the better decisions our pricing engines can make for better rider-driver experience and marketplace efficiency. So one way we're approaching it with machine learning is in an offline-online way. We look at historical events. We try to find familiar patterns. We can use a supervised classification technique, random forest example here, to find what these patterns and these families of patterns look like, and then feed them into our online real-time models that can adapt and learn from these patterns. And we create a feedback loop. As new events occur, we learn about them and feed them back into our real-time systems. So that allows us to anticipate these shocks to the marketplace. There was an event back in June in San Francisco. It wasn't quite on all of our radars, but it's clear from the data here, there are patterns, unique patterns. Peaks, valleys, peaks again, Friday, Saturday, Sunday. Could be nightlife, could be something else. We looked at this, and it happened to be a comedy festival. Some of you might have attended. It was a comedy festival in the Civic Center area. And while it wasn't quite on our radar, we need to be able to anticipate this because clearly people in San Francisco wanted to get there. And if you look deeper, there are actually more granular patterns. This is when Kevin Hart was doing his routine, and Bill Burr and Jerry Seinfeld. And clearly, there are different patterns for even these different comedians. How do we learn about this in real time and anticipate it? So what's really difficult in this problem space? It's easy to look at shocks in the past, measure their impact, and then put it into a model. That's fine. But how do we actually do this before they happen? How do we predict something days ahead before the shock to the marketplace occurs? And how do we do it in scenarios where we don't have training data, where there's no historical data? And how do we transfer learnings from cities? Or as Wally put it, leverage the human intuition by the hundreds of operations folks that Uber has in all of our cities. So this is where we're looking at deep learning and doing research in this area to enable this. Forecasting, you can look at the past to predict the future. We're leveraging LSTMs in an encoder-decoder architecture to model the various factors, both internal and external to the marketplace, to help us learn about these systems and learn about these embeddings. Typically, this type of architecture has been used for machine translation problems. But we've found with the collaboration with our AI labs team that they're actually great for space-time problems as well. And so the way we look at it is we pull external signals from the outside world, holiday, weather, events, even spatial information. We generate embeddings through convolutional networks or autoencoding techniques, and we pass these through our system. And when we look at models like this, for example, going back to the Super Bowl, we can see massive reductions in error for things we didn't quite understand or had full training data on. Our naive models could look at the recent past or last few Super Bowls, 15 to 20% weighted error. With these types of models, we can get down to 5%, and that's great. Why? Because it allows better decisions. Better models will lead to better decisions for the riders, the drivers, and the efficiency of the marketplace. So speaking of riders, Uber has a rich offering of products, and those products can be delivered to our riders in different types of contexts. Some rider, and this could be overwhelming for a rider too. We have economy, UberX and Pool, premium, select and black, extra seats, XL and SUVs, and there's probably things that I'm not even aware of. How do we deliver a unique and personalized experience to groups of riders? Well, this is where we have to leverage ML too. And by using ML, because the feature space is massive, because the product offerings are massive, and because the experiences that we can create are numerous, we leverage ML to create a personalized experience and reduce friction points. So here you have John and Sally. John uses Uber Pool to get to and from work. He stops by Tartine on the way too. Sally, she goes to the airport. She travels a lot for work, and she uses Uber Select to get to the airport, and she grabs a pastry from Tartine on the way to the airport. In these feed cards, in different pieces of your app, we leverage machine learning across all the features, across these products, to give personalized destination recommendations, to give personalized request cards, and even in John's case, offer a subscription pass to help with this commute. We look at machine learning to measure also the effects of personalization rather than directly modeling outcomes. And similar to uplift modeling, where we look at groups of riders and see the types of features and experiences that work well for them. And it allows us, with machine learning here, we can model an incremental conversion by delivering the right experiences at the right time for groups of riders. So here we have groups of riders, many, many hundreds of groups of riders, thousands of features that are sort of measured in terms of their importance. And here we use a set of ensembling models where it's a combination of gradient boosted trees, neural networks, and random forests to generate sort of an incremental conversion curve, to then deliver the right experience to the riders at the right time. But how do we also enable the experiences that are best for our drivers? Well, we talked about this one really important piece of Uber, dispatch. And you may have seen when you're requesting for a ride, there's that car that's just one block away from you. You're like, why didn't I get that car? Why was the car like 4 blocks away? Who's had that experience? All right. So you would think, why don't we match the closest car to the rider? Well, there's a variety of reasons. One driver could have a high ETA. They could be leaving that AT&T park, that Giants game at AT&T Park that Walida was talking about. And they may be stuck in traffic, even though they're a block or two away. Or they may be just on the wrong side of Market Street and they have to take many turns to get to the other side. That's not a great experience for the driver or the rider. We have drivers that could be on the highway. You know San Francisco, it takes forever to get anywhere. To get off the highway, to get to you, to navigate the streets, it may not be an efficient experience. You have to wait. Even though, imagine seeing that closest driver matched to you, but then seeing the ETA change. Like, that's not great. But more importantly for our drivers, there's a great feature that we have that allows drivers to set their preferred destination when they want to head home. If I'm a rider in San Francisco, and I want to go to Oakland, should we match to a driver who wants to head home back to San Jose? This is also to think about the driver's experience. So in dispatch, we have a flow. We look at rider's request. You see that spinner icon show up when we're finding that rider-driver match. And the goal is really to maximize driver and rider satisfaction. And here we have to use machine learning because the dimensionality of this problem is massive. And these decisions have to be made in real time to achieve the maximum rider and driver satisfaction. We take input features like ETA, demand levels, trip distance, and we leverage this and many, many more features with recent and historical data across an ensemble of models again. And this is to optimize that rider-driver match for the different scenarios we talked about. But the scenarios are compelling here because the scenarios are not rules. The scenarios are around a dynamically changing physical world. How do we learn about this and make these decisions in real time? We can't do it any other way except machine learning. Simple model architecture where we're taking data from our pipelines using a modeling service. And because dispatch is real time, we have to make 15,000 or more predictions every second with the lag, SLA of 100 milliseconds. It's a very difficult problem to get right every time. And this is what makes the problems in Marketplace and Uber as a whole extremely difficult and challenging, but exciting, more exciting than anything I've seen personally. It's a space-time product and other dimensional problem. To give you a sense of that physicality of the problem, we operate in more than 600 cities. The atomic spatial units are hexagons. We have more than 10,000 of these in every city. We have many products. We generate many inferences per minute across many quantities and many, many models. To give you a sense of how then do we industrialize machine learning to build the best models that allow the marketplace to make the best decisions for the riders, the drivers, and the efficiency for Uber. Today, we're generating more than 5 billion real-time forecasts every minute. Why so many? Because we do it down to a hyper-local granular level. And we make decisions for the marketplace at that hyper-local level. Dispatch is doing 30 million plus dispatch pair predictions a minute in real time. We have to get this right. We focus on scale, reliability, and accuracy. And even the systems we're building leverage machine learning to heal themselves, to scale up, to deploy models without human intervention. So this is what's exciting about Marketplace and the way we're using machine learning. It's a problem that hasn't been solved before. That's what Uber is trying to solve. And in Marketplace, we build these models and we teach these models more and more about our marketplace. But through machine learning, we want our models to be able to teach us. We want our models to teach us about the marketplace to enable the best rider and driver experience.